slightly different, so we appreciate your flexibility in meeting us here in one of our smaller conference rooms. Welcome to UCR Palm Desert. My name is Agal Patel, the Executive Director right here, and I'm so happy to welcome you to our second Science Lecture Series event hosted in partnership with our friends at College of Natural and Agricultural Sciences. Two of the lectures, this is the second one. You heard the first one last month. We're going to have two more in Riverside, so if you're inclined to come out and see us in Riverside, there's one in April and then one in May as well. You can pick up information outside. We'd love to see you out there as well. Each science lecture topic tackles some of the most pressing issues we face as a local, national, and a global community, from climate science to subatomic particles, to supporting sustainable agriculture and water management practices. The 2025 lecture series will be sure to keep you apprised on all of those pressing needs. Special shout out to my friend and colleague Joanne Young, who has helped me tirelessly over the last few years to program these out here at UCR Palm Desert. You know her and Dean Atkinson are committed to the Coachella Valley, and we appreciate their support. Before we bring up Peter up on the stage, please let me go over a few upcoming events happening right here. It's going to be a busy March, folks, so I'll be quizzing some of you out there on what's coming up. We've got 2 this week, 4 next week, and 3 more the following week, so it's a busy March. On Thursday, right here, with our friends at the School of Medicine Pediatric Clinic, we are bringing My Health, My Voice, studies on Parkinson's diseases with Dr. Philippe from UC Irvine, who's going to talk about clinical research as well as client opportunities. So that's happening. That's a 2-part series kicking off this Thursday. On the 10th, we'll be featuring part of our American Stone documentary series featuring William Wyler, the French documentarian, who was behind some notable films like Dead Her. We're going to be featuring his documentary right here on Monday. Upon the 11th, the third and final in our partnership with our friends at the Functional Spine Committee, we're going to be featuring Janice Loud and Sydney Williams, who will present an entertaining look at the complicated 3-year process of shepherding the Palm Springs School book project to completion. So that's going to be a widely popular event. On the 12th, the final in our biomedical lecture series, I saw a number of you come with us to the trip we made last week to our simulation center in Riverside, so thank you for attending. But on the 12th, we're going to be featuring Professor Seema Woodruff, who will talk about cutting-edge research on multiple sclerosis and training legends. So mark your calendars for that as well. On the 13th, the second in our Boyd Deep Canyon research, against part of our CNAS program, featuring Greg Tolley, who is the Natural History Museum of Los Angeles, who is from the Natural History of Los Angeles County, talking about the ecological consequences of using rat poisoning, which is very important, of course, for our environment. And I preserve the printers. On the 18th, part of our Wild Coachella, the final one, we're going to be featuring Professor and researcher Dr. Jessica Hopkins, who will discuss the unique challenges and opportunities posed by the climate changes in the inland desert region. So another important science topic. On the 19th, we're switching gears and partnering with our friends at College of Humanities, Arts, and Social Sciences, our Arts and Letters program featuring author Rachel Housel Hall, who you will remember her from last year. She's a New York Times bestseller. The new book, the last one, has gotten rave reviews and has been Good Morning America's book club just a few months ago. So that's on the 19th, and on the 20th, we are going to be bringing Tim Lyons and his friends and researchers back on the We Are Not Alone lecture series, this time featuring Emma Edison on the impacts of the drying sulfur seeds. So all of that and much, much more, I hope you can take notes in the month of March. So pick up a flyer outside. And if you are a Palm Desert 7 partner, please you raise your hand. I see a number of you out here. Thank you for your generosity. Thank you for your support today. It's Gift Day. It's an important day for all of us. If you haven't had a chance to look at that, please look at that and support our various initiatives, including Friends of the College of Natural and Agricultural Sciences. And speaking of CNS, why don't we bring up Peter here? Peter is a professor of genetics in the Department of Entomology, joined UCR in 1997, and prior to his tenure, Peter was a senior research scientist at the Commonwealth Scientific and Industrial Research Organizations in Canberra, Australia. First generation college student, earning his PhD and a DS with honors from the University of Melbourne in Australia. Since joining Riverside, Atkinson has served in a number of administrative roles within the college, campus, and the University of California system. He has served as Deputy Interim Director of the Institute of Integrative Genome Biology, Director of Interdepartmental Graduate Program in Cell, Molecular, and Development Biology, Director of the Center for Vector Research, Chair of the Institutional Biosafety Committee, Divisional Dean of Life Sciences, on, and the Chair and Senate Committee of Planning and Budget. So all of this to say that's his official bio. Unofficially, he's a strong supporter of everything we do out here in the Coachella Valley. Please welcome D. Atkinson.
Well, thanks, and it's wonderful to come out here. We drive up to Riverside. It's a beautiful drive. It's a beautiful area. And what's really significant by this audience and all the audiences beforehand is that you helped create this hub of science and technology of interest. And what I've noticed and applauded since we've resurrected this science series this year and last year after the pandemic, and when I was Life Science Dean 10 years ago, just 5 years, we came out here quite regularly, and it was always a pleasure to come out to such a tremble audience and inform. And what we're trying to do, and we'll be back next year, is to come up with a series of themes and sometimes lectures, seminars, which are general or specific interest, which reflects what we do in the College of Natural and Agricultural Sciences. It's unique in the UC system in that it's the only college of science that have all the sciences up for one umbrella. If you go to the other UCs, Berkeley, Los Angeles, etc., you'll find colleges or schools of life sciences and physical science at Davis. So we have it all in one shop. And it's a fantastic advantage for us because as science becomes more interdisciplinary, we'll see biophysicists working with life scientists, working with botany, botanists. I was talking this morning down at the convention center in downtown Riverside on science, and it was a fantastic event showing scientific interactions between ourselves in the college and colleagues in the School of Engineering, and then colleagues from engineering schools from 5 other universities across the country, all sponsored by NSF, and all focused on preserving biological material. But enough of that. This is fantastic. We'll be back next year. Thanks again for coming down as you attend week. So this evening's lecture is going to be by Dr. Miguel Arratia. He's an assistant professor, so he's moderately new to UCR. In the Department of Physics and Astronomy. And he'll give his presentation on the title, Quantum Tomography, Mapping the Inner World of the Atomic Nucleus with a New Type of Particle Collider. Something different from Mary Joyce last month on animal fossils in outback Australia. Quite different, but it shows the breadth of what we do when we, not these, as our brilliant faculty, students, staff do. Dr. Arratia will discuss his research in mapping the structure of the atomic nucleus through quantum tomography, seeking to understand how it arises from the most fundamental particles. And some of you may remember early physics courses of Ernest Rutherford, initially at the University of Manchester and then at Cambridge, coming up with that fairly simplistic model of the atom way back then. A very small nucleus and a big patch of nothingness, if you will, and these talking his language to having the electrons circling outside. And so we're going to see a peek into what that nucleus really does. Central to his work is the future Electron-Ion Collider, a flagship facility for nuclear physics currently under construction in Long Island, New York. This first of its kind collider will allow us to study how quantum particles such as quarks, gluons, arrange themselves in space-time to form protons, neutrons, and atomic nuclei, which of course we remember from middle school, the essential blocks of matter. These studies may help us unravel the origins of quantum spin, mass, and other properties of the proton. Miguel Arratia specializes in experimental particle and nuclear physics. Previous to his appointment as an assistant professor at the Department of Physics and Astronomy, he was a postdoctoral fellow at UC Berkeley to the north of us and earned his PhD from the University of Cambridge in the United Kingdom. His research focuses on using high-energy electron beams to probe the atomic nucleus. His probe designs, this is what he does. He designs, he builds, and he tests new detector technologies for future experiments, including those at the Electron-Ion Collider, currently under construction in Long Island. So please join me in welcoming Dr. Arratia to the parade.
More right. Joe. Thank you very much. Can you hear it well? Is that? All right. Thank you very much. I'm very happy to be here. Thank you for coming. So I will talk about the nucleus, and I will tell you why you should care. But first, let me just tell you, I will also show quick pictures saying how you might have it. And the idea of my talk is twofold. I will describe a very new particle collider. It's a big, big project that is underlying, is under construction. We are preparing for it. I will tell you the big ideas, the goals, this experiment or this new project. Then in the second part of my talk, I will bring it down to earth. So no science goals and concepts, projects that are too big, but actually we're there to bring it down to the actual classroom. I will show you the work that our students do in order to develop the technology that will enable future discoveries in this future experiments. And the second part, so I will start with something very general, perhaps too general. Everything is made out of atoms. You and me, everything we know about the universe, everything is atoms. Not only that, but we know that the atoms have a nucleus, as Peter said, was discovered in the Rutherford 100 years ago or so, and it hard 20 years ago. So the atomic nucleus itself is made out of other things that are smaller. Those things are what we call fundamental building blocks, a fundamental particles. Those are called quarks and gluons. So that is in a nutshell. So that is statement that everything is made out of atoms, and nuclei is made out of protons and neutrons, and those are made out of quarks and gluons. One sentence, you code a lot of information, like many, many centuries of discoveries in physics. So if we have to save just one sentence or one piece of knowledge, it would be a good candidate for the physics point of view. So I will show you a little video just to illustrate that. I mean, this is just a cartoon where they have the nucleus orbiting around the electrons, but if you zoom in, then ultimately you're going to have like other things that are more real. And again, the quantum level, we have particles that are popping in and out of existence. And those are the real fundamental blocks that make everything, including UFB. And so that's what we're going to see this lecture. Those are the main participants that you would view it. So the atomic nucleus is made out of protons.
as I said before, protons and neutrons. That's what makes everything. But the proton itself is not an elementary particle. It's made out of something else, and that something else is very complex. I don't want to give you the impression that this is a very simple picture. It's actually a dynamical picture that I'm going to visualize right now. So on the left-hand side is an artistic impression. This was made by an artist visualizing how that artist conceived of the proton. It's made out of many different particles. And that entire system, that dense system, somehow makes the nucleus. So, but it's not just a picture like the artist depicted. I will show you a video. This is actually a very recent video made by my colleagues at MIT and Jefferson Laboratory, describing how the proton actually looks like. If you were able to look at the proton at a very microscopic level and in a very fast way, this is what you would see. So the proton, depending on how fast you look at it, it might be have a camera that is very fast. Depending on how fast the camera is, you're going to be able to resolve the quantum level particles that are coming in and out of existence. So these things are not static like all these, and the proton really is the net result of all of those interactions. It's a dynamic system, it's a dense system, and it has these fundamental particles dancing, swirling around. And that is what makes us. It's not just, actually this visualization is coming from real data, from experiments that we can transform from data we take from these experiments into visualizations that makes more sense than just a graph. But this is the type of research that I want to do, is visualizing exactly how is the structure of the proton when you look at it at the most fundamental level, the quantum level. So that is the modern view of the proton. So let me introduce to you the elementary particles. So everything we know, as I told you before, is made out of elementary particles. For some reason that we don't understand, there are a limited number of them, and you can put them in a graph like this. It's like a periodic table. But instead of a periodic table of elegance, this is a periodic table of fundamental particles. So there are families of different type of particles. Here is what we call the quarks. These are the ones that make a proton. These ones are called leptons. Names don't matter, but the electron is the most famous of them, and we use electrons for electricity, electronics. That's one type of elementary particle. And we have all the particles that are the ones that are responsible for the forces of nature, like gravity, electromagnetism, or the nuclear force. The one that is responsible for the nuclear force, the strong nuclear force, we call gluon. That is that. So basically, the atomic nucleus is made out of quarks and gluons that are binding the quarks together. That's it. So these are our basic ingredients. As far as we know, these particles are completely elementary. They are not made of anything else. They are point-like, so they have no size. This is a concept, of course, that goes beyond what we can perceive. But bear in mind, bear with me a little bit. So we have to take the word for it. Take my word for it. There is no size involved in this particle. These particles have all the properties like charge. Electron has charge. That's what electricity is. Electron moving around. But all the particles have charge too. And they have mass. And they have other properties like a spin. I will describe in a little bit what spin is. So spin is a fundamental property of particles. The electron has a spin. So what is a spin? As the name suggests, which physicists like simple names, as the name suggests, this is a property that is analogous of a charge moving, rotating, or spinning. When you have a charge that spins, then you create a magnetic field. So think of it as a little magnet that has a north pole and a south pole. So charges that are moving, rotating, create magnets that, from electromagnetism. So the electrons have this north-south pole. embedded into them. It's like an inherent property. That's what we call a spin. The spin is not as known as the charge of electrons, like electronics, the field of electronics, and the field of electricity deals with the charge of electrons. That's what enables our modern society. The spin is not a property that has been as impactful just yet. People are working hard on it. I have colleagues in the department who are working in spintronics. So manipulating the spin of the electron. The promise for that is, in principle, you can create a quantum computing. Quantum computer, which is a new generation of different type of computers that are going to be much more powerful than classical computers. So that is something that the spin of the electron could give us in the future. It's an important property. But the analogy of this of rotating electrons falls short, because as far as we know, there is nothing rotating. The electrons have no size, and nothing is rotating. It's just as if they have an inherent magnet associated with them. Each little electron, each electron that we see, each electron that we ever measured, has exactly the same magnetic field. And it has a magnet that you can manipulate and you can measure very precisely the way I've done that. It's just a property of them. Just like electrons. So this is a property that is very hard to visualize in our everyday experience, but it's very important to understand because we have, it brings us tools to do practical applications, but also it brings us a tool that we can explore to look into the structure of the atomic nucleus itself. So it's a tool for exploration, scientific domain too. In particular, because the protons, which makes you and me, also have spins. We know this since about 100 years ago. It was discovered that the protons have spin, meaning that they behave as if they are rotating and have a little magnet associated with them. We can measure them. So if you put a proton in a magnetic field, they react because they are like aligning magnets in a magnetic field. Actually, that has also practical applications. You may have experienced magnetic resonance imaging, MRI, like that's used in medicine. That technique, MRI, is using the spin of the protons. It's aligning the protons that are inside the body to get a signal of the density of your interior to make a picture of you without breaking you apart. So we already know how to use the spin. That technique was discovered about 50 years ago and is very useful. But the truth is, we do not know how the proton spin actually originates. Because the spin of the proton is not just a fundamental cycle of nature, because the proton is not an elementary party. The proton, as I was showing you before, is made up of quarks and gluons, which is a very dynamic system. Many different quarks and gluons, each of them has its own spin, and somehow that entire system conspires to give us the proton spin, the magnitude that we measure. Every single proton that we ever measured, that is in everything in the universe, is exactly the same size. The spin, the magnitude is the same. We don't know why that number is what it is. We don't know how the system evolves so that happens. And that is a mystery that we need to resolve. And so this is an important quest, a scientific exploration, because even though we already know how to use proton spin, even today in medicine, MRI, that's proton spin applications, we don't really know the origin. So the analogy that I'd like to use is like, you can use fire as a tool or as a weapon without understanding how fire actually works, like how fire is created. And that's fine. We should use that. But if you were to know exactly how fire works, how it emerges, then you are able to better control fire and better improve the tool associated with the fire technology that went led in the history of civilization to energy sources or you know this. I mean, I don't have to explain this to you. But the same reason, in my view, motivates why we should care about how spin actually works, as opposed to just using it. So that's one of the motivations why we want to do this. Maybe in the far future, if we understand how the proton spin originates, we might be able to manipulate it better, create better cases. Just like electron spin has a bright future in quantum computing, it's not hard to imagine that perhaps in the future we can manipulate proton spin and do cool things. This is in the far future. Okay. For now, this is just scientific exploration, purely scientific. So the key concept that I want to describe to you today is the concept of emergence, what we physicists call emergence. But it's a concept that you know for sure, and which is that the concept of the whole is greater than the sum of its parts. Okay? So if I tell you that the proton is made up of quarks and gluons, I am not telling you much. The same way that if I tell you that the brain is made out of neurons, that doesn't tell you how a brain works. That's a true statement. The brain is made out of neurons, but you need to know how the neurons arrange themselves, how they interact, and then you can start understanding the brain. That's the concept of emergence. The same thing with the ocean. I can tell you the ocean is made out of water, and that is a true statement. But if you want to understand the currents and the dynamic processes that are in the ocean, you need to understand, the concept of how currents interact and the energy system that is driving them. So in the same way, we need to go beyond the simple statement that the proton is made of quarks and gluons. We need to know exactly how they arrange themselves, exactly how they interact, and exactly the dynamics of the system that leads to the properties of the proton. So that is what we need to do in order to fully understand what a proton is, how it emerges from those interactions. So if we were to know, we would be able to know how the mass of the proton is what it is. Mass is an important property. We have weight because we have mass. From where that mass is coming from? It's coming from the mass of the proton. Like 99% of your mass is coming from mass of the protons and neutrons. We don't really know from where that's coming from, because what makes the protons, these quarks and gluons that I showed you, they have zero mass or near zero mass. Somehow, when there are many of them, the interactions of those quarks and gluons, not their masses themselves, but their interactions, the dynamics creates mass. And that is our mass, the Earth's mass, the universe mass. Yeah. It's really a problem. If we crack the code on how much emerges from the proton, we will understand the origin of mass in the entire universe. The same thing with spin, as I show you. There's also a question why the proton is the size that it has. We don't know. And we don't know the pressure. The size of the proton is probably the highest pressure in the universe. Even higher than the pressure inside big stars. Inside each one of those protons inside your body, the pressure that is inside is unimaginable. It's much greater than in the stars. And that has to do with the fact that they are so much dense. Protons are so much small, but they have so much energy concentrated in that volume that the pressures are extremely high. And that's what we want to explore. Good. This is my only slide that has an equation, I promise. I wanted to show you the exact detail about what we want to measure. Then this has to do with quantum mechanics, and it has to do with the density of the proton in terms of quarks and gluons, meaning how they are distributed in space, how dense the protons are in space, in 3D space, and how fast they are moving. And we can encode that information at the quantum level, which is the ultimate description of nature, in a simple function that you can write down in one line. It's not super complicated, but that is it. We want to measure that thing. And how do you measure that thing? It's actually depicted in the right-hand side diagram. What we have is electrons, is that we are able to use as probes of the atomic nucleus. So if you have a high energy electrons, the electrons shine light on the nucleus. Like this is literally the case. Electrons can radiate, they can emit light. Not visible light like what we see with our eyes, but light that is much, much more energetic with much shorter wavelength. And because of that, it's able to restore 5 features of the atomic nucleus at the quark gluon level, at the fundamental particle level. So we need electrons, high energy electrons. To get them, we need high, powerful accelerators. And that's what we call quantum tomography. Is electron beams colliding with nucleus, with the atomic nucleus. And then we see how those electrons scatter depending on how they fly around in different directions and with different energies. We are able to reconstruct the mathematical function that I showed you before, which is the quantum description of the atomic nucleus. We not only need electrons, but remember electrons have tiny magnets associated with them, just like the nucleus. We need a particle acceleration that is able to control those little magnets. This is illustrated in this diagram. So these arrows represent the little magnets associated with the nucleus or the electron. That is not easy, but it can be done because accelerators are made with electric and magnetic fields, and with electric and magnetic fields, you can manipulate the orientation of magnets. That's possible. So we need an accelerator that can do that. No particle accelerator ever in the history of particle accelerators, which started around the 50s, has ever been able to do that, to manipulate the magnets, the properties of the magnets of the particles that are colliding. We have never had that before, but we absolutely need that if we want to explore what is the origin of spin. And that is this new project that motivates this new project called the Electron-Ion Collider. So the Electron-Ion Collider is shown at the cartoon on the left-hand side. So this is going to be located in Brookhaven National Laboratory, which is located in Long Island, New York. This is a map, just to give you a sense of the scale. These are a bunch of buildings. So this is a big ring tunnels that are going to host accelerators that are in a ring, 2.4 miles in circumference. And particles are going to rotate around this ring, being accelerated faster and faster and faster before they collide. And we are able to run the experiments that I will describe in a second. So this is just a diagram illustrating what the Electron-Ion Collider will be. But it's actually a real project in the sense that it started officially in 2020. This is a picture of the ribbon cutting ceremony. You can perhaps recognize a few famous people from New York, senators and governors. This started in 2020, and the pandemic, you can see, because of the masks. But it's actually going to take a long time before we see this in reality, because it's a big project, 2.4 mile circumference accelerator. It has a big price tag. It's $3 billion over a decade of construction. But this will happen in the 2030s. So I'm very excited about that. I will describe what is the current status, or we've been calling goals. Fortunately for us physicists, the Electron-Ion Collider is never starting from scratch. We can reuse a previous generation particle collider. That's what's called CRIC. This is a real picture, and this is a real picture of what it looks like. So today there is already a particle collider, 2.4 miles circumference, that is there. Is not the right type for the experiments that we want to do, but at least partially we can reuse all that infrastructure. We don't need to create a new tunnel. We can reuse many things, and that brings our project closer to reality. Okay, so this is how it would look like. This is what it looks like already on the right-hand side. So long tunnels with magnets, and where particles are moving at that and accelerated, so that they go faster and faster. Very famous. So the collisions of the Electron-Ion Collider will look like something like this. So you have the electron-ion collider. This is from above. You have particles that are going to go in one of those rings, that the yellow ring are just going round and around, very close to the speed of light, very, very fast. And you have all the particles that are going in the opposite direction. And those beams of particles are going to collide or cross at a specific point. That's where we run the experiments. Okay? So that's the idea. This is how a particle accelerator works. You may wonder, why do you need this to be so big? 2.4 circumference. The reason is, the bigger the collider, the higher the energy you can achieve. Like the particles will go faster. They will just go faster and faster. So that is the reason. We need energy in order to resolve the atomic nucleus features with higher and higher precision. That. So the key questions motivating the EAC, this I just took from the official project. This is basically what I was describing before. Let me just read a few of them. So we need to know, how do subatomic building blocks with virtually no mass interact to produce the mass of a proton, as well as we see in the universe? So the mass, origin of mass. What is the origin of mass? We will try to find out. What is the origin of the strong nuclear force? That's the second question. If we study the quarks and gluons that are making the nucleus, we hope to understand how the atomic force, the nuclear force itself, originates. And the third question is, how is the spin of the proton originating? That's another question. So big questions. And we are hoping that new discoveries in this machine that's going to start next decade and run for tens and like dozens of years will help us address some of this. So in a nutshell, the history of my field can be summarized in this cartoon. Back in the 80s, well, there is a history. Back in the 80s, we knew that protons were made out of quarks, and people thought maybe what is making the proton is really in three quarks. And those quarks have little magnets, the spin, that are aligned in a way that they add up to the proton spin. And that's it. And those quarks are going to be bounded by these little springs that are representing gluons. That's what excited the 80s. But then experiments were run in the 90s, 2000s, and the picture became more complicated. It's not as simple as having three quarks. You need much more of this swarm of elementary particles to account for the experimental data. So it's not a picture that we just jumped into this because we liked it and it's pretty. It's just the data forced us to move to a more complicated picture. In the 2030s, we might find out that actually this few quarks with a few gluons is not going to make it. We really need to account for the large number of gluons that are popping in and out of existence. That might be the clue of what is the origin of all the properties of the proton, and therefore all the properties of the atomic nucleus. So that's what we're going towards that direction. As I showed you before, the Electron-Ion Collider has detectors. So when these two rings intersect, that is where collisions occur. So two beams of particles colliding. That's where we put detectors around and we run our experiments. So I will describe that in a second. So what a detector looks like. This is what it looks like. It's not in reality because we haven't built it yet, but this is how a detector looks like. Just to give you a scale, I put a bus here. So they are pretty big, and unlike a bus, every inch of this detector is filled with electronics and with detector materials and cables. It's a very complex thing. It has like a cylindrical structure, a cylindrical shape, but it's made out of like an onion, in the sense that you have different layers. At the center is where the collisions occur. You have a layer that is a technology that measures certain aspect of the particles that are created. Then a different layer will measure something else, complementary to what you measured before. Then you have more and more and more layers. So that's what we do in particle nuclear physics. These are the instruments that we deal with, that we use in order to run our experiments. This doesn't fit in a lab. It's a very large detector, and we need a specialized infrastructure to run that. So we don't have the Electron-Ion Collider yet, but we actually, my group this year developed a virtual reality tool to actually bring it to life. This is available for free. You can try it out. Actually, I will give you a link in case you or your kids know how to use this type of thing, virtual reality. It's usually jaw-dropping because there's some students here, they're visiting my lab, we tested this, and they love it. What I will show you is a video using this tool, which is bringing this new detector to life. It's not going to be as cool as looking at a virtual reality that allows you to see this in real life size, but the still is pretty good. I will show you in a second. This is a video which was also produced by my group, and it's going to show you what the experiment actually looks like. What we are going to see in very realistic terms, actually, how data looks like once we take it. Yeah. This is a cool using time at least we have the detector. Then at the center, where the particle collisions occur, when you have this high articulation, so particles are going to be created, and that's what we measure. So this is a visualization of the detector, but for simplified, each color represents different layers of the onion. And what we want is really to have as much data as we can from the particles that are emanating from the particle collision, and then we can reconstruct what happened. So that's the main idea. And this is what we think the data will look like. So bunch of spray of things that are going to come out of our reactions. Then we need to join the dots to try to see what actually emerges. Again, the bus here, just to show you the sense of the scale, these are big instruments. They work like a giant camera. We want to explore take pictures basically of what's occurring. So this is the actual data, what it will look like. I could give you a bit more details how we are going to build this. And we designed and tested some of the instruments that are going to go into this big detector. Damn it. So this is a cross-section of the detector. So if you were to split the detector in half, you open the onion, this is what you would see. This is of course a cartoon. Different colors are representing different detectors. And I'm going to show you the design and test of a few of them. In particular, the ones that are in the region. That near, this is where particles go, like along this axis, and they collide at the center. Proton beams are going from left to right, electron beams from right to left. So we are going to see some detectors that are going in the proton-to-ion direction, and this is the one in a series of many of the detectors that we have designed and tested at USCAR. So the first one we call the calorimeter, just in honor to our great state, right? It's called the calorimeter cluster. It's a detector that looks like this, and it's located in the forward region, like the disc that is closing the cylinder of the detector that I showed you before. So what is this detector about? Each little cell that you can see in there are many cells, is made out of plastic, special type of plastic that emits light, and particularly blue light, when radiation hits them. When radiation excites the plastic, it has some special molecules, and that emit light. Then we couple those plastic scintillators, they're called scintillators, with photosensors that can count how many photons of light, particles of light we see. So if you combine those two, you have like a building block for a detector, and then what you do is to combine layers of heavy stuff, what we call absorber, iron, with material that detects light. So you have layers, absorber, detection, absorber, detection, and so on. So this is what we designed. We thought this would be a good idea, a nice trick in order to really measure what is the energy, the particles that are hitting the detector when they are created conditions. Turns out that our detector is going to get exposed to a lot of radiation. So it's bad. It's bad for humans, but it's also bad for electronics. Electronics doesn't like when it's irradiated. It just gets damaged, corrupted. And this plot is just showing you the map heat map about where radiation is the worst. And the red is the region where we are, and that's the worst part to begin. So we have to design the detectors that is sustained itself. Like it can work even after being heavily irradiated. So that is one of the challenges we had to overcome. So we had to design this around, and we needed to retest these building blocks and make sure that those detector building blocks are going to be resilient enough to survive this radiation. So this is how this looks in reality, down to earth again. This is one of my students holding one of those little tiles. So the scale, just this is this big, so not very large. That when we use is something called cosmic rays. So this is our last setup. But what we use is cosmic rays, which are particles that are coming from outer space, going through the atmosphere and everywhere. They hit everywhere, including right now at this moment, there are hundreds, thousands, tens of thousands of cosmic rays passing through us. We don't notice them. But if you have sensitive instruments, you are able to detect them. And because they are raining down, we don't need an accelerator to produce high energy particles. They are just raining down from the heaven. So we use them in order to know what happens with our little plastics that we made at UCR and on the photosensors, how much signal they get. And this is data that's showing you how much signal we get from a single particle passing through. And we had to design the detector and optimize the shape and how we build this thing in order to be as sensitive to a signal as possible. Then we needed to actually do an experiment with an actual particle accelerator to see how our sensors are going to survive the radiation environment. Like the UC Davis has a cyclotron, it's a particle accelerator. That's a relic from the Cold War era. And it's still operating because that thing is useful for many things. If you want to irradiate chips or do other stuff, you go to a particle accelerator and see how the chips are resilient to radiation damage, because in space you get radiation too. So we went there, we ran an experiment, these are my students, and we irradiated what we needed in order to make sure that they will survive. And the answer is yes, they survived, and the design that we're going to use accounts for the fact that they're going to get damaged, but not entirely broken. Then what we need to do was to make prototypes. We had an idea for a particle detector. Then we need to actually make it a reality. So that means constructing a little version of like the one to construct in the future. So these are just pictures on how actually this process works. Right? It has to do with CLC, like machines that are cutting plastic or the shapes that we need. And then we make lots of them, and then we use those to create layers, but in miniature scale. So this is like, you can see the scale because one of my students called me. This is small scale. We want just to make small versions of the detectors that we're going to build that are very large ultimately. So we tested this. So this is our first prototype in 2023. These are the proud students around this detector that is here. It's actually a very little detector. So it's like this big area. And it is like 40 kilometers. It's like a baby in the weight. And this was the origin of our Cinderella story. We started with just a small idea about how we're going to make a very big detector. And at the time, people were not convinced, they didn't know about this method, so we had to convince our colleagues that this actually worked. So this is why we built this at UCR. After we built it, we moved to a national laboratory where they have a big accelerator. So here my students installing the detector in this experimental area. A particle beam will go from here all the way and hit our detector. And we want to see how it's going to work. This is like mimicking how it's going to operate in the real experiment in the future. So we did that experiment. This is January 2023. At that time, small detector, and we took data. And so this is what the data looks like. I will not go into details about the data, but the thing that you want to know is that we have data that's actually the measurement, and we have simulation, meaning a computer simulation of what the detector should see. And we compared data, which is in blue, with simulation. The blue and the orange are on top of each other. That means that what we designed works as we expect. That is the first step. We had a little detector, works as we expected, gives us confidence, and then the next step is to scale up. So we built a better, bigger version of what we tested before. So this is what we call generation 2 detector. So the detector number 1 was there. Big Brother is just a bigger version of it, better improved. We designed this in a way that made it better. And this is how it looks in reality in a lab in UCR. So this is made out, as I said before, of iron blocks. These are square blocks. And then we have this hexagon plastic scintillators and photosensors that detect the light that particles create when they hit part detector. So we had generation 2. We did the same, but in a different laboratory. We did bring our detector into an actual particle accelerator that is operating right now. This is RIC, a RIC accelerator that is a predecessor of the Electron-Ion Collider. This is what an experiment adaptation looks like. It's on 2 of our students. They installed a detector in a place where there was nothing around, so there was some free space, and we could run our own experiment in a particle collider. That is actually very cool from our point of view anyway. And this is how it looks like. From the center of the collisions, this is where our detector is located, so you can see it. From our detector looking at the center of the collision, we have like a free shot, like particles that are going to be created in the collision are going to stream through air and hit our detector. So that's the idea. So particles are created, they fly around, they hit our detectors. We want to see and measure what our detector records. And the same story repeated again. We have data in red, simulation in blue. We have some data that matches simulation reasonably well. So that means that our detector works as expected under realistic conditions. We validated the technology. We convinced ourselves that we can build this. And the next step is again to scale up. So we scaled the big detector into a bigger version. So now the detector now looks like this. So instead of having just one little square, you have an area that is 9 times bigger. And this tech is just heavier. It has more detector units, more cells. And these are some of the students building them. So this is really down to earth. They work with their hands to build this thing in the lab, put it together. This is how it looks at the end. They have the students there. When repeating the story, we do bring our technology prototype into a particle accelerator. Again, this actually last month, February 2025, in Jefferson Lab again, because our detector installed, ready to take data. We're ready to get a beam, high energy beam of particles right in the middle of it. And then we are going to be able to see whether it works, the scales, like what we expect. This is not just a repeat of what we did before. At every step in the design process, we optimize, we improve, and we confirm that our expectations match reality. So this is just a snapshot. In the last few years, it started a little big brother to a bigger brother, and it's a factor of 10 more in channels and complexity. So at that time, 2023, we were not really taken seriously because there was a new idea that we had to pitch to our colleagues. And this time, we had a lot of data to back our design. So we were able to convince our colleagues that actually this is a good idea, this is good works nicely. So they took our idea and they scaled it. They did scale it tremendously. So this is the entire detector that has 600,000 channels. It's going to be made like we composed with these little scintillators that focus sensors. So we scaled from 40 channels to 800, and now we only need to do that 1,000 times to scale to this thing. We are going to need a little bit of help, a few friends along the way, but it's going to happen, and this is what we are doing right now. So this is detector is funded and it's under construction. So there's an item Cinderella story. We could have ended there, because it was a very quite big chunk of hardware that we got. But we didn't do it. We doubled down. So our success story motivated us to double down and go after all the detectors. So we proposed the same technology that we had developed for a different type of detector. This is a more specialized detector that is called zero-emission detector. It is located tucked in between magnets. These are where particles go, and it's a very small detector. Generally speaking, this is 60 centimeters by 60 centimeters, and the area is like this big. But it's located in a very strategic position. And so we said, we're going to use the same technology, but this detector, because this is the right technology to use, we're going to be able to build it and do all the stuff with it. And this is how the detector will look like. This we're going to build with technologies entirely at the CR. This is actually the real size. You can see, get a sense of how it is with the students there. And this is built in a modular way, just like we had before done for smaller prototypes. We just stack it together, just like Legos, one on top of the other. And there's a replication cycle that allows us to scale up the production of the detector and make it with as many channels as possible. And just like the cameras, your detector and your phones, the more pixels you have, the better the camera. So that's why we want to have as many channels as possible. So this is the road. It has been a bumpy road, but ultimately we have been succeeding scaling up the detector technology that we have been using, all designed, built, tested by UCR students, particularly undergrad students, many of them working along their studies. So in summary, the message like I hope have conveyed to you that looking for the structure of the proton and the atomic nucleus is worth our endeavor, and the Electron-Ion Collider is our dream machine and is becoming a reality. And the second point I want to stress, and the third point that I want to stress, the summary, is that using Riverside students are designing, building, and testing the technologies that are going to enable this new experiments. So with that, thank you very much.
Wow. That is simple. So just open to questions from the audience. Please raise your hand and try and walk around as if you are tomography. Right.
Well, congratulations. Of course. So you can now take a look at the proton. What about the neutron?
That's an excellent question. So we do both. We do both. They are the two sides of the same coin. In our view, we need to understand the proton, but also the neutron at the same level. So how do we do that is because neutrons have no charge. Because they don't have charge, they cannot be accelerated. So you cannot have a beam of neutrons in the accelerator. But we do play tricks like accelerate an isotope of hydrogen that has a proton vanishes to a neutron. That's what we call an P-theory. It's an isotope of hydrogen. And you can also accelerate that because it has a charge of the proton. So the Electron-Ion Collider collides protons, but also accelerates neutrons. And the neutrons is like our proxy to study neutrons. For sure, we need to study that. We do that precisely in the capability exists. So that's now a way to support them in. Thank you.
Use the time. Oh, agree. There's a fantastic talk. So I have a couple of questions. One, when it came to particle accelerators, they always started small, lower energies, lower accelerations and size. Is this the first electron-ion collider to exist? Have there not been smaller scale versions ever built?
Yeah, that's an excellent question. I didn't stress that enough. This is going to be the first electron-ion collider in history. So there are many types of accelerators that have existed before. Particle colliders, they collided protons with protons, or heavy ions, or heavy nucleus, like lead with lead, or electrons with electrons, but never electrons with protons. We have never done that before, okay? And the reason for that is twofold. There are technology challenges to do that, because the beams are not the same. One is electron, the other is proton, and that creates an imbalance in the accelerator that is hard to handle that. So it's more challenging. With the other aspect is that the other type of colliders, like proton-proton colliders, they are used in a different way. They are used to look for new elementary particles. We are not interested in that in this type of vector. We are really interested in exploring the nature of the proton itself and to discover new particles, which is a different type of accelerator needed. This is why I call the Electron-Ion Collider a collider of a new type. It's literally going to be in the first one in history. Because of that, the discovery potentials of this accelerator is huge because we've never done it. So whatever we do is going to be new. And history tells us that when you do something new, you discover new things. So that's why we are so excited about it.
Okay, so don't make a black hole that destroys the kind of swallows it. No, the other question that I had is, what do you expect to see? Are there any favorite hypotheses that you believe could, be confirmed as the origin of the spin property of proton? Do you have an idea of what interrelationship, what forces, what kind of things are going on inside the proton amongst the quarks and lepton, by the quarks and gluons?
Yes.
That takes to cause spin to emerge. And do you have sort of a favorite hypothesis?
That's an excellent question. So there are the hypothesis at the beginning was in the 80s, let's say, was that the spin of the proton was just the spin, intrinsic spin of the quarks. Because we know quarks have spin, we actually can measure that. So we know the spin of the quarks, we know that there are more or less 3 quarks that carry most of the energy in the proton. So we said, maybe that's where the spin is coming from. Then that hypothesis was ruled out. So what else can it be? Now, gluons, that is a new thing. Gluons have a spin too. And there are many, many gluons. And those gluons are orbiting around, just like planets orbit the sun. I think, sorry, a bit weird, so I know where it's coming from, the distractings. But just like it's easy, the gluons actually can rotate around the proton. And if they rotate in a coordinated way, just the orbital motion of them can generate the spin of the proton. So that's one of the hypotheses we want to test, whether it is really coming from the orbital motion, something that is rotating in a coordinated manner. And all of this is really at the quantum level. So there is something called a entanglement, which is a quantum property, it's a weird phenomenon that is occurring in quantum physics. And we believe that also has a certain role to play. Like these particles are just like meteor balls moving around. They are connected in a fundamental sense with each other. Like every particle is connected through quantum mechanics to all the others. And that process also can, in a coherent fashion, build up a proton spin. That's another hypothesis that we want to test.
Cool. My question is about where does acceleration, collision start and fission begin?
So that's a great question. So you have, should be, let me show you how the diagram was here. The center, please. Look. There you go. So, the accelerator complex is big. Okay, so this is 2.5 or 2.4 miles. This comes this vision. But here you can see a smaller circle, and even a smaller circle. And then if you were to between, there is a smaller circle. So everything starts in a very small accelerator. Let's say something you can put in a thing. Okay, that's the origin. That's where we get hydrogen to, which is ocean, which are protons. And then you strip hydrogen, like they strip the electrons out of hydrogen to just have it float, not bounded with the electrons. So charged hydrogen, you can accelerate that with a small energies, with a small accelerator. But then you inject that current of hydrogen into a bigger accelerator, and that brings it to another level of phenomenon. Then you do the same with that bigger accelerator. So you can inject when you got into another bigger acceleration and jump can you do that again and again? So how the beams start is actually from very humble beginnings. What tabletop source hits. When the particles collide is where these two things intersect with. So in this point and at that point, like a 6 of that and then theta thought. We call them that IT6 or IT8, just is a word. And they connect at those, so at those positions you have magnets, specialized magnets that can bend the beams and steer them precisely so that they collide. So we only have those magnets in those locations and nowhere else. So everywhere else they just go around and around and around. And they continue going around until you keep feeding more and more particles to get more and more collisions. So that is a never-ending process. You can keep going. It's just a matter of running the machine takes energy, time. So that's why you didn't stop. That's the only thing it is.
One other question. When MRIs are done, they were originally called nuclear magnetic radiation, when patient didn't like that word. So they changed it to MRI. Same technique. Now, we use high energy Tesla magnets to actually stop the rotation of protons and cause every proton in your body to come to attention. And then the computer reads the effect of the magnetic field being withdrawn and how those protons come to life. And that's how we represent the tissue that we look at relative to water. So why aren't you using external sources of magnetism to gain the same kind of information?
That's an excellent question, and you described the MRI much better than what I did. But let me tell you that we do what you said, in the sense that we do use magnetic fields, external magnetic fields, to align the protons, just like an MRI. Because you need to do that. Wait, this is the cartoon they show you at the beginning. Races. Sure. You need the spin to align them in a given manner. So we need control over the spin of the protons, just like an MRI. And we do that with magnetic fields. In the accelerator, there are specialized magnetic fields that are moving the protons in the right direction. The magnetic intrinsic spin of the protons aligning them. We do the same thing with the electrons. So when we do experiment, we very much control where the proton spin and electron spin are pointing to. We can control that the same way that you control MRI. And just the same way, I just wanted to mention something about, you're completely right that at the beginning, when the technology was invented in the 50s, they had the word nuclear in it. And they removed that word because of negative connotations, and the technique is the same. The same thing happens in this detector, in this collider. Like ion, it's just a fancy word for nucleus. But nucleus had negative connotations, so people wanted to stay away from that. So what we are going to throw that the politically correct word is ion, and that's why we are called Electron-Ion Collider. It has not nuclear in it. You should, because we're just in nuclear physics and we have nuclear beams. But that's scarcely.
Curtis Baptist, technically countable one.
Professor, thank you for the amazing talk. I had actually two questions. Firstly, I know that on my practice slide a few weeks ago, is that the intrinsic spin of an electron is like the constant equal to 2. Is the intrinsic spin of a proton the same, or is a higher spin particle? Because I know if you were right, because I know they're in that at least the way I mapped it out, the higher spin particles get more common in the kind of almost the conference.
So that's an excellent question. Both actually have a spin in the right units, in physicists units, which are natural units, is 1/2.
Okay.
So both have a spin 1/2. The answer is, the question is, why is it that they have spin 1/2? And every single proton we have ever measured, in every material that we have seen, has exactly the same spin. Exactly the same. And that measured the right units is 1/2. We don't know from where that number is coming from. It could have been any number, but just is 1/2. There has to be a reason why is 1/2, and we want to find out why on time. That's the motivation for this type of study. We know the answer. This is kind of a different problem scientifically. We already know the answer, the numerical answer, but we don't know how we ended up there. I think the answer is 1/2. I can give you that. You can measure that. You can use it for MRI, but we don't know why that number is what it is. It could have been, as far as we know, it could have been MNB. So that's a mystery.
And then something that's like related to that, like, oh, on those graphics that you were showing that showed the particle collisions, it looked very, I guess, like neat and like visually like clear. But I know that like from seeing some of the map with how uncertain, how you get quantum levels.
Yes. Yeah, but the data actually, what I showed you in the videos is actually real data. It's not simply like simulated. It's not real in the sense that we took the experiment, but it's the best representation given our computer simulations on how the data will look like. We didn't simplify it at all. It looks pretty because it is pretty. Like it just happens to be a given. The experiment produces beautiful data with interesting patterns that your brain actually can decode. Our brains are extremely good at exploiting patterns in these reactions. You can see clusters of energy here, cluster unit there. If you then analyze that from a physics point of view, you can take that data and encode it into equations. We can use a theory to constrain parameters in theory based on the data. So that's where the magic happens. But the data itself is very simple. It's just pixels, dots in detectors. And it's exactly what you saw. It's not more complicated than that. Then the real work, what the more complicated work is to translate that into mathematical insight. That is more complicated. And I didn't go through it because it's too much fun. Let me put aside and work with them.
One last question.
Coming from a humanities person and a science person, a couple of questions. Maybe you explain this, I just pressed it. The device that was made here at Riverside by the students and by you, is that going to be transported to New York and incorporated in this machine? Or to do your work, are you going to have to go to New York to obtain the data from this machine, form it in the data you read, and then go use the readings? And that's what my third general question will be. In his work after he developed the theory of relativity and special relativity, Einstein spent the rest of his life trying to develop a unified theory of the universe. Is your work doing anything in that regard to move further toward a unified theory?
Okay, I will start with the set of questions. So what we did at UCR when the student built were prototypes. Just like imagine you're building a big plane. Don't start with the plane right away. You build something really smaller by the scale. Test, let's say, waiting tunnel, and you then see how it works. And then you are going to build bigger versions. That's how engineering works. It's not going from nothing to the big bang. Okay? So what we did was the smaller prototypes, and what we are going to do in the next years is to scale that up even further. And ultimately, we're going to be building just about 1,000 times bigger than what we built already. And we are going to install that in Berkeley National Lab. That's where the particle accelerator is in New York. We don't have a particle accelerator in UCR, otherwise we would do the experiment there. But you build things here that we transport them to New York. Just we run the experiment there, so my students and myself will be traveling a lot, doing the experiment, taking the data, we can start with our data, analyze it, share this field. That's how it works in practice. Now, your question about the unification, that's a great point. The unification of physics, of fundamental physics, I should say, is really trying to unify, in essence, elementary particles that we have. So we have actually 5 different forces. We have gravity, We have the strong nuclear force, we have the electromagnetic force, you have the weak nuclear force. There are 4 forces. For each force, we have one particle associated with that. Einstein and many others have said 4 is too many. We would like to have one force that is like the master force of that is, or the modern force that ends up in 4 different forces. And in order to do that, they stipulated or made theories that actually there are more elementary particles that we know about today, and there are others that we haven't seen, and that might be evidence that there is only one force, not 4. So the quest to look for unification of forces involves trying to make and find evidence for new elementary particles. That's what it boils down to. This research is not geared towards that quest. We say, this is our building block, our periodic table. We're happy with that, with the knowledge we had. Now we want to build upon that. Like, how actually are our building blocks arranging to create us, like the atomic nucleus? My colleagues are looking for new particles. That's a very active area of research, but it's not exactly what I'm doing. It's related in the sense we use different similar concepts. We use accelerators, we use detectors, we run the same type of experiments, but it's a different type.
Okay, thanks, Miguel. And what Miguel is way too polite to say is that the building that he works in was active in 1960. So he's building this advanced equipment that will be ultimately transported to New York and to do the experiments that he describes. That building, the opening in 1962 means that it was designed in the 1950s and instructions started in the late 1950s. So at a time when nuclear physics in the United States and elsewhere was sort of in its pinnacle. We are working very hard at UCR to right now start planning about 4 new physics building. We still need state budgets to come, so we'll turn around but use ahead. But it's a very high priority for us. He talked about his work. There are others in the papers. There are also building detectors for other reasons, other areas of physics. But we're very lucky at UCR and able to therefore can tell about the talented physicists and astronomers are asking questions about the fundamental nature of the power. So please join with me and thank you. Well, students. Visits to this venue, we will be back next academic year. We'll be working to see when we can best get all the talks and figure out what to present here. We'd like your feedback about that and what you'd like to have. Please let us know. We do have 2 more science lectures left in this series, so I'll be down on our campus in Riverside. The next will be after the 12th. The Lucy Blaine, who's a professor and teacher in the Department of Evolutionary Ecology and Physical Biology, and it was really what is an organism really like. Lucy, I've actually had the honor to teach with Lucy first year on the molecular biology spike chemistry that learned these, so I think it is one fantastic presenter and educator like you with that. So thanks again for your hospitality. Feedback is appreciated, also ideas for talks and likes here from our faculty on any topic, whether they're local or beyond international, in this case, encompassing the entire universe that we know. In fact, thanks for your time. You're a bit of an effort to come out here. I would really do appreciate it because just please remember that UC Riverside is your UC. And please use it, visit us. It's yours. Please let us know how you feel about it. I was politically very proud to be part of your year. And thanks a lot. It's fun time.